Newton's law of cooling. Forensics investigators use Newton's law of cooling during murder investigations to discover the time of a victim's death. Building designers use rates of heat transfer and cooling of different substances to choose insulation. Workers in the food industry need to know rates of temperature transfer for heating, cooling, and storing food. Newton's law of cooling states the rate of change of temperature of an object or substance occurs in proportion to its surrounding ambient temperature. By knowing an object's initial temperature, current temperature, and the surrounding temperature, a constant and a temperature-time correlation can be figured. In this lab, finding these values involves utilizing differential equations. The rate of temperature change can be found with the following equations. The change in temperature is equal to a constant of decline times the current temperature of the substance minus the ambient temperature. Temperature changes over time are equal to an ambient temperature plus an initial temperature minus the ambient temperature multiplied by the exponential function of our declining constant and the change in time. For this experiment, we need 3 cups of water, 1 or more thermometers, 1 timer, and 1 method of recording our data. For this trial, we will add hot, cold, and room temperature water to each of our 3 cups and measure their initial temperatures. We will also monitor temperature changes over time. For this trial, we'll take measurements every 15 minutes. The results will be plotted in a line graph for a visual representation of the exponential rate of temperature change. Hi Josh, we're here today studying Newton's law of cooling, and what have we got?
We have 3 different cups of water, each with a different temperature of water in it. This one, the hot cup of water, this one, the room temperature, and this one, the cold.
And what are we going to do with these cups of water, Josh?
We're going to use this to measure the temperature in each different cup of water. And you can measure the temperature at set intervals, and we can use the formula for thermal cooling to predict the temperature changes over time.
Okay, Josh, what do we need for our formula?
We need a few measurements over time to plug into the formula to determine the constant.
Great, get to it.
Alright.
Our temperature values measured early on can be used to calculate the constant for a given formula to predict temperature changes over time. Get to it. Continue to take measurements at 15-minute intervals to compare the measured results with the predictions derived from the formula. Plugging in initial measured values into our formula, we arrive at a constant of 0.0355. With our constant, we can calculate the time needed for the water to cool to equilibrium with the room temperature. Plugging into the formula, cooling to equilibrium will take 246.78 minutes. So JJ, we've done our measurements, we've got our numbers. What did we find?
Well, as we predicted, the water changed proportionately to the differences from the surrounding air. The hot water changed more dramatically in the beginning of the experiment because its initial temperature was further from the ambient air.
Great. Theoretically, the formula for hot water cooling can also be used to calculate the heat gained by the cold water. The time calculated to reach equilibrium should be the same because the two volumes of water are controlled under the same conditions. However, the plotted points on the graph look different, and our recorded temperatures show a slightly different rate of change over time. Why might this have occurred? So, JJ, how well does the equation with our constant predict temperature changes over time, like reaching equilibrium?
Well, the measured temperature at the predicted time for the hot water cooling to equilibrium was 0.9 degrees warmer than the measured room temperature. This is about a 1.4% percentile margin of error. It's kind of, yeah. So if we use the same prediction for the cooling of not the cooling, but the warming of the cold water, we find about a 6.5 degree difference from the measured water temperature. So experimental conditions may have been less controlled for that sample. For this lab, the hot water was brought to its boiling point. Boiling temperature on this day was 99.6 degrees Celsius. However, the initial measured temperature had cooled to 89 degrees Celsius in the cup due to the rapid rate of initial cooling. The cold water began at its freezing point, 0.0 degrees Celsius. Room temperature on this day was 24.4 degrees Celsius. The charted results show that both the hot water and the cold water experienced an exponential rate of temperature change, though the hot water's greater temperature difference from room temperature produced more visible results early on. As expected, the ambient temperature remained relatively constant. Using the formula to calculate the rate of cooling, the hot water should have cooled to room temperature after just under 247 minutes. Looking at the graph of our actual measured water temperature near that time, we can estimate a water temperature of 25.3 degrees Celsius. Newton's law of cooling states that a substance's temperature will change at a rate relative to the difference of that of their surroundings. Overall, the graph shows that heat gained by the cold water was more gradual, while cooling of the hot water, at least initially, was more dramatic. The calculated difference of 0.9 degrees Celsius between the projected amount of time for the hot water to reach equilibrium and the actual measured temperature at that time is an acceptable 1.4% margin of error. It should be noted, though, after 375 minutes, the heated water was still 0.2 degrees Celsius above room temperature. The differences in calculated and measured values can be attributed to variables out of the experimental control and those not accounted for. For example, barometric pressure and ambient humidity could not be controlled in this lab environment, and the shape of water containers and thus surface area of the liquid was not accounted for. Evaporation throughout the experiment and
the presence of solid ice in the cold water likely influence results in unexpected ways as well. Newton's law of cooling states that substances will experience a rate of temperature change equal to the temperature difference between the substance and that of their surroundings. Therefore, the greater the difference between the temperature of a substance and the ambient temperature relatively, the more pronounced the rate of change will be. This is why the cold water yielded a more gradual rate of temperature change. The initial difference between the cold water, 0.0 degrees Celsius, and the ambient temperature, 24.4 degrees Celsius, was less than that between the hot water, 89 degrees Celsius, and the ambient temperature. Again, 24.4 degrees Celsius. Ready? Mm-hmm. So, JJ, we got some good data. What's next?
Well, what's next is we can run trials and settings with different ambient temperatures, hotter or colder. We can also try to experiment with different containers, better insulated containers, or containers that present the water with different amounts of surface area.
Great, thanks.
You're welcome. You seriously done?